Hello, students. Today we are going to continue our discussion that we started about thermodynamics. In the last class, we have talked about the process of calorimetry, and we knew how the bomb calorimeter can be used to determine the change in the enthalpy and the internal energy of a specific process under constant volume and under constant pressure. So, in thermodynamics, in the last class, we have also solved several numerical problems to see how we can efficiently calculate or measure these properties that are delta H and delta U. In last class, in these two problems I solved, first one was regarding sucrose and the second was regarding this water evaporation and carbon or graphite combustion. And we saw how a Q calorimeter, that is the heat gained by a calorimeter, is related to Q reaction, that is the reaction heat or the heat of the reaction. And then we tried to calculate the Q reaction in terms of mole just by dividing the amount of substrate present, dividing by it by the molecular weight of the substance. So now we will move forward to our today's discussion. So in today's discussion, we will try to have a brief idea on enthalpy change, that is delta RH of a reaction, or popularly it is known as the reaction enthalpy. So we'll start our today's discussion with reaction enthalpy. So this is called also the enthalpies of reaction. Now, to one way to report the heat absorbed or released would be a compile of a massive set of reference table. A reference table will be that, and that will list the enthalpy change for all the possible chemical reaction. But that would require an incredible amount of effort. As you know, we have some millions and trillions of chemical compounds, and many undergo some billions and trillions number of reactions. Now, there will be some massive compiling set of a reference table to see what are the enthalpy changes of a specific reaction. Now, all we have to know what is the initial state and what is the final state, because enthalpy is a state function. I have already discussed this with you, that internal energy and enthalpy, all of these are state function. So fortunately, our effort of listing up a huge table will be cut short. So we have to know about the initial state, that is stage initial, and the final state, that is stage final of the chemical reaction. And then we can be allowed to calculate the enthalpy change for a chemical process virtually by any conceivable chemical reaction using a small set of tabulated data. So we need specifically a very small set of data. And since enthalpy is a state function, let me just bring up the pen over here. Since enthalpy is a state function, so its value does not depend on the path or the route that is taken up, but its value does not depend on the path. So it is state function. So we need very little amount of tabulated data in form of this table that you are seeing over here. These are the enthalpies of vaporization and fusion for selective substances at their boiling points and at their melting points. So we have different parameters, like you can see over here. First one is the enthalpy of combustion, that is termed as delta H combustion. Combustion means it is burnt off in air. So a change in enthalpy that occurs during a combustion reaction. A combustion reaction means I have got a substrate. Now I have to heat it completely or burn it off completely in presence of ideal oxygen. That is called a combustion reaction. Now, enthalpy changes have been measured for the combustion of virtually any substance that will be burned in oxygen. So that is in air. These values are usually reported as the enthalpy of combustion per mole of the substance. Next in line, we have delta H fusion, that is enthalpy of fusion. Fusion means melting. So the enthalpy change that accompanies the melting of 1 mole of a substance, that is called the enthalpy of fusion. the enthalpy change that is accompanied by melting or fusion of 1 mole of substance. These values have been measured for almost all the elements of most of the simple compounds. These values are available. Next, we have enthalpy of vaporization. So, vaporization means it will be evaporated or it will be vaporized. So, the enthalpy change that accompanies the vaporization of 1 mole of substance, that is called the enthalpy of vaporization. So, for all the elements and for most of the volatile compounds means which are vaporized quite easily. For example, naphthalene. Naphthalene is an aromatic hydrocarbon that is easily volatile. And lastly, we have enthalpy of solution, that is delta H solution. A change in enthalpy when that occurs when a specific amount of heat or solute dissolves in a given quantity of solvent. Now, the enthalpy change when a specific amount of solute is dissolved in a given quantity of solvent, that is called the delta H solution. Suppose we have sodium chloride, that is table salt. It is readily available in our household. Now we have a glass of water which is having a volume of, say, 10 ml. And we have NaCl whose weight is around, let's say, 1 gram. So 1 gram of NaCl is now put into this 10 ml glass of water. And so a specific solute is now dissolved in a solvent. So when the change in enthalpy, now the change in enthalpy when NaCl 1 gram is dissolved in those 10 ml of water, that is called the delta H solution of NaCl. So likewise, we can define the different enthalpy value: delta H combustion, delta H fusion, delta H vaporization, delta H solution, and so on. Now there is a table for your good understanding. First one, we have substance, that is argon, delta H vaporization and delta H fusion. Both are given in the unit of kilojoule per mole. You see, for argon, which is an inert gas, you see from the periodic table, you see argon is on the extreme right hand side. That is the inert gas group it belongs to. So we have argon, which is an inert gas. The delta H vaporization of an inert gas, that is argon, is 6.3 kilojoule per mole, and delta H fusion is 1.3 kilojoule per mole. So for argon, it is 6.3. Now we have methane, CH4. Delta H vaporization of methane is 9.2 kilojoule per mole, and delta H fusion is 0.84 kilojoule per mole. You see over here, there is a clear difference in the delta H vaporization of argon and methane. So if we compare the delta H vaporization, that is the vaporization enthalpy of these two compounds, argon and methane, you see argon is quite low, and for delta vaporization of methane is quite high. Why is it so? The answer is lying within, if you have read about the periodic table. In periodic table, you know argon belongs to the inert gas group. In case of inert gas, they have the electronic configuration of NS2 NP6. Means both of their s orbitals and p orbitals are completely filled. So they do not need any other electrons to form the inter-electronic attraction. In this case, in case of argon, since it is an inert gas, so there is minimal intermolecular interaction because it is already satisfied by its own electronic configuration. That is NH2 NP6, its octet is completely filled. And that's why in case of iron, there is minimal interaction between two argon atom or molecule. We know there will be very much less van der Waals attraction between the argon molecules. And since the van der Waals attraction between the argon atoms is very much low, that's why we will require less amount of energy or enthalpy to vaporize this. And that's why the delta E vaporization of argon is much less than that of methane. Actually, delta E vaporization of argon, that is the inert gas, will be lower than any other gas that we will be discussing over here. You see here, in case of argon, the delta E vaporization is 6.3. But in all these cases, whether it is methane or it is ethanol, it is benzene, or it is water, or it is mercury, or it is iron, the delta H vaporization is much, much higher. You see over here, we have these two as gas. And for gases, the delta H vaporization will be low. In case of liquid, the delta H vaporization will be a bit higher. So that's why in case of ethanol, benzene, and water, you see the delta H vaporization value is much more. Ethanol has a delta vaporization value as 39.3, benzene has 31, and water has 47. Why water has the highest delta vaporization? That you can guess, because water, you see, can perform extensive hydrogen bonding network within the water molecules. And that's why its delta vaporization will be much higher. Likewise, in case of ethanol also, the extent of hydrogen bonding is much, but not obviously more than water. That's why it is delta vaporization is 39.3. And also in case of benzene, which is an aromatic hydrocarbon which does not have any polar hydrogen. And that's why it is unable to perform any hydrogen bonding network with the similar benzene molecules. And that's why its delta vaporization is less than that of ethanol and water. And next in line, we have two solids. They are mercury and iron. These are transition elements which are actually metals, and they are solid. Since they are solid, we need much more energy to vaporize them. You see, their delta vaporization values are quite high. Iron has 59.0, mercury has 59.0, and iron has a quite high delta vaporization, that is 340 kilojoule per mole. So likewise, we can actually predict or assume which kinds of substances will have high delta H vaporization value or the enthalpy of fusion. You can also see over here, in case of delta H fusion, that is melting of a substance, the melting process is not as straightforward as vaporization. And here also you can see, in case of the melting case, the iron has the highest value and methane has the lowest value. I've also collected some specific enthalpy change data for fusion and vaporization. So we have substances like N2, NH3, HCl, CO, acetone, carbon tetrachloride, water, sodium chloride, and benzene. Now TF and TB are their corresponding melting and boiling point. For melting point, it is termed as FTF because F stands for fusion, that is melting. And B stands for boiling. So we have substances N2, ammonia, HCl, carbon monoxide, that is carbonyl, acetone, carbon tetrachloride, water, sodium chloride, and benzene. Between among all these things, you have the TF, that is the melting point. You see, the melting point of NaCl is the largest among all these components. That is more than 1000 Kelvin. The melting point of N2, that is dinitrogen, is the lowest, is 63.15. If you have a clear look at the delta H fusion value in kilojoule per mole, you see among all these values, the value of nitrogen is the lowest, that is 0.72. here also the explanation comes just like from the argon case. You know that nitrogen is all nitrogen, though it falls in group 15, but dinitrogen acts as an inert gas. Because in dinitrogen, two of the nitrogen molecules, nitrogen atoms, are connected to each other by three very strong bonds. There is a triple bond between these two nitrogen atoms. One is sigma, and the other two are pi bonds. And the bond reduction energy of a dinitrogen molecule is quite high. It is even more than 800 to 900 kilojoule per mole. And that's why to break this bond between two nitrogen and to make it fused, that is liquid, the value is quite low, that is 0.72. The same thing also is reflected in the delta H vaporization also. You see, among all the molecules over here, in case of dinitrogen, the delta H vaporization value is the lowest one, that is 5.59 kilojoule per mole. If you can see, can look at the other substances, you see from nitrogen to CO, all these are gases. Nitrogen is a gas, ammonia is also a gas, which has a delta H vaporization 23.35. Now a question may arise, why in case of ammonia and HCl, though they are gases, their delta H vaporization value is quite larger than these two gases? Because you see, we have two sets of gas. One has N2 and CO. And the other two gases are ammonia and HCl. Ammonia and HCl delta H vaporization value are quite high, 23 and 16 respectively. But in case of nitrogen and CO, the values are quite less. You see, one is 5.59 and the other one is 6.04. But in case of ammonia and HCl, that is NH3 and HCl, hydrogen chloride gas, the values are quite high. What is the reason behind it? Because in this case also, the hydrogen bonding parameter comes into picture. In case of N2 and CO, you see there is no polar hydrogen present in the molecule. That's why there is no intermolecular hydrogen bonding present in dinitrogen and carbon monoxide. But in case of ammonia and HCl, since we have polar hydrogens present, in case of ammonia, we have three polar hydrogens. In case of hydrogen chloride, we have a polar hydrogen, and they are capable of performing or undergoing intermolecular hydrogen bonding. And that's why, because they are intermolecularly hydrogen bonded and their network is quite vast, so there will be more requirement of energy to vaporize these gases. That's why ammonia and HCl have a higher delta H vaporization value. Now, in next in line, we have three liquids: acetone, carbon tetrachloride, and water. And obviously, these liquids have a higher delta H vaporization value than the gas one, because we know, because of the owing to the presence of intermolecular attraction, we separate or segregate between the states of matter in which the intermolecular attraction is highest. They are called the solids. Next in line, which has a lesser amount of hydrogen bonding network, they are called the liquid or intermolecular attraction. And next we have gases, which have very much less amount of intermolecular attraction or interaction. So when it is already a gas, then less energy will be required to vaporize it. When it is liquid, there will be a little bit larger energy to vaporize it. And when it will be solid, we have to first make it liquid, then we have to make it a gas, and then we need to vaporize this. So in case of solid, the value will be highest. And that is reflected here in case of delta H fusion and delta H vaporization. You see, in case of NaCl, the delta H fusion value is the largest one, that is around 29. And in case of NaCl also, the delta H vaporization is also the largest one. which is 170 kilojoule per mole, that is highest. So now we have three liquids. One is acetone, other one is CCl4, and the last one is water. As we have anticipated in case of water also, just like we said in the last class, the intermolecular interaction by the network of hydrogen bonding is highest in case of water. So it will have the highest delta H vaporization value. Now you can ask a similar question, why in case of acetone the value is not the higher one? Because you see in case of acetone, though there are hydrogen atoms present, but they are not polar enough to undergo hydrogen bonding. If I draw the structure of acetone over here, this is acetone, CH3CO, CH3. But you see over here, in case of acetone, these hydrogens are bonded to a sp3 carbon atom. And that's why they are not polar enough to undergo hydrogen bonding with other acetone molecule. And that's why in case of acetone, the delta vaporization value is lower, that is 29.1. In case of benzene also, you can see the same. You see, in case of benzene, benzene is an aromatic hydrocarbon which has 6 hydrogen atoms. But all of these hydrogen atoms are connected to an sp2 hybridized carbon atom. That's why the benzene hydrogen atoms are not that much acidic. And to perform hydrogen bonding, the hydrogen should be connected to any of the electronegative atoms, that is nitrogen, oxygen, chlorine, and in some cases, Cl. That's why in case of water, when hydrogen is directly bonded to oxygen, it performs very extensive hydrogen bonding. And similarly, ammonia and HF all undergo very extensive hydrogen bonding, which results in its higher boiling point. So in case of benzene and acetone, since their hydrogens are not connected to electronegative atoms and they are not polar, so intermolecular hydrogen bonding is completely absent over there. That's why their delta H vaporization value will be much lower with respect to water. But all are surpassed by sodium chloride, which is a solid Na plus and Cl minus. It is an ionic compound. And since it is an ionic compound, very much high energy is required to either melt it or vaporize it. That's why in case of NaCl, you see the values are highest as for delta H fusion and also for delta H vaporization. So here are some standard molar enthalpies of formation of delta F H minus at 298 Kelvin of a few selected substance. Before we go deeper into all these cases, we will have a brief introduction introduction about the reaction enthalpy. Now, let us think about a chemical reaction where we have reactants on the left hand side and we have products. On the right hand side. Now, when the reactants will be converted into products, the enthalpy change accompanying a reaction is called the reaction enthalpy. So, it is written as del RH, where R will be in the subscript of the delta and it will be squeezed in between delta and H. H stands for enthalpy, delta stands for the change in the enthalpy, and R stands for the reaction. So del RH tells us it is a reaction enthalpy. So delta RH is equal to sum of the enthalpies of the product minus sum of the enthalpies of the reactants. So if we can mathematically introduce this term del RH, we have this equation summation of I AI into H of product. That is the enthalpy of product. P stands for product. I will write it as PR dot minus summation of BI into H of reactant. This is the mathematical expression for calculating the reaction enthalpy del RH, summation of AI H of product minus summation of BI H of reactants. The symbol summation, or it is called the capital sigma. We have two sigmas. One is the small sigma for the designation of a sigma bond, and we have a capital sigma that is required to present the summation of or the addition of several units or components. AI and BI are the stoichiometric coefficients of the product and the reactants in the balanced chemical equation. So if I give you a classical example, you will understand it better that what is AI and BI, what is meant by the stoichiometric coefficient of reactants and the products. So we have, let's take up a classical reaction, that is combustion of methane in oxygen. So firstly, we will write the reaction and then we will try to balance it. Because whenever we will talk about reactions, we have to first balance it and then we will be able to calculate the coefficient, the delta Ng and etc. So methane is a gas, CH4 gas. It will be burnt in oxygen, which is also a gas. And any hydrocarbon, as you know, if it is burnt in air, it will produce carbon dioxide, which is CO2, and it forms water, that is a liquid. So now we will try to balance this equation. We have CH4 plus O2 to CO2 plus H2O. Now, on the left-hand side, we have two oxygen atoms. On the right-hand side, we have three oxygen atoms. So now we will be able to balance it. So let's suppose we are putting a 2 over here for balancing. It will be 4 oxygen atoms. But then on the right-hand side, still, we have 3 oxygen atoms. So now if we put a 2 over here ahead of water, we have 2 oxygen and 2 oxygen from CO2. So we have 4 oxygen on the right-hand side. We have 4 oxygen on the left-hand side. Here also, we have 4 hydrogen atoms, 2 into 2. Here also, we have 4 hydrogen atoms. So here also on the left-hand side, we have 1 carbon. On the right-hand side also, we have 1 carbon. So now this entire equation has been balanced. Now, if we have to calculate the delta RH of the reaction, how we can be able to calculate it? So if we write del RH of this reaction, we have summation of AI of H of product minus summation of BI into H of the reactants. Now we have on the right hand side, that is the product side. On product side, we have CO2 and H2O. So we have the H molar enthalpy, which is HM of the CO2 gas. Plus, because we have to add up, the summation sign stands for we have to add all the components on the product side minus we have to add the component of all the components in the reactant side. So in the product side, we have CO2 and H2O. The CO2 part is done. Now we have the H2O part. For H2O part, we have 2 moles of H2O. So it will be already multiplied by 2. So 2 into H molar of H2O liquid. So this is the right hand side where we have H molar of CO2 gas plus 2 into H molar of H2O liquid. Then we have to minus the or subtract the
Recording in progress.
plus we have a dioxygen molecule over here. So we will thus multiply it 2 because it is the stoichiometric coefficient for oxygen. So it is 2 into H molar of O2 gas. Now each molar for all the components stands for the reaction of molar enthalpy of each of these component we are talking about. Here we have 4 components: methane, oxygen, CO2 and water. On the product side, we have CO2 and water. That's why they are written first. And on the left hand side, it's the reactant side, we have methane and dioxygen. So it will be 2 into H molar of O2 gas. So del R H is actually equal to HM, that is the H molar of CO2 gas plus 2 into H molar of H2O liquid. We will subtract HM of methane gas, that is the reactant side, the first reactant, and the second reactant is oxygen. We will multiply it by the stoichiometric coefficient. That's why we have to make sure we have to first balance any chemical equation that we are using. So finally, we have got the value, that is delta RH, as this expression. Now, enthalpy change of a reaction is a very much useful quantity because the knowledge of its quantity is required when we need to plan the heating or cooling to maintain the industrial chemical reaction at a constant temperature. If we have in mind what is the del RH of a reaction, we can pre-plan like how we need to cool the reaction or we need to heat up the reaction. If delta RH is positive, that means it is an exothermic reaction, so we need to cool it down. And if it is endothermic, that means it is required some heat, so we have to put some heat into the reaction externally. It is also required to calculate the temperature dependence of an equilibrium constant. But for that, we will be discussing on some other classes. So let's now focus on our standard enthalpy of a reaction. The enthalpy of a reaction depends on the condition under which a reaction is carried out. So that is very much pivotal in this case. The standard enthalpy of a reaction is the enthalpy change for a reaction when all the participating substances are in their standard state. Now the question may arise, what is meant by the standard state? The standard state of a substance is at a specified temperature, is its pure form at 1 bar. The standard state. So standard state of a substance at a specified temperature, that is capital T, is its pure form at 1 bar. So at 1 bar of atmospheric pressure at a given T, the pure form of the compound is called the standard state. So for example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. The standard state of solid iron at 500 Kelvin is pure iron at 1 bar. Usually, for our convenience, the data at which the T value is taken is 25 degrees Celsius. Usually. So usually at 298 Kelvin, the pure form of the component at 1 bar of atmospheric pressure is called the standard state. The standard conditions are denoted by adding the superscript of minus at the symbol of delta H. So for determining or denoting the standard state, we will use this symbol, that is delta H, but a minus inside a circle will be used. So this symbol is important. Delta H minus, that is called the standard enthalpy of reaction. Now enthalpy changes will be occurring during the phase transformation. You see, for these many slides I have told you about fusion, about vaporization, all these are phase transformation. You see, if a molecule, that is A, if it goes from solid to liquid, it is a phase transformation. Or it is now going from a gas to solid, this is also a phase transformation. So phase transformations are actually involving energy change. From solid to liquid, we are going from one phase to another. That is a phase transformation. For a classical example, you can take up as ice, which is known to every one of you. Ice, for example, requires heat for melting. We have H2O solid. That is ice. Now it requires heat for melting. So for phase transformation, the heat is required. That is delta is required. Normally, this melting takes place at constant atmospheric pressure, that is 1 bar, and during phase change, the temperature remains constant at 273 Kelvin, that is 0 degrees Celsius. So this is a phase transformation or phase change from H2O solid to H2O liquid. So we have the delta H fusion for this. The delta fusion H, and since it is in a standard state, it will be delta fusion H minus. The value of this is 6 kilojoule per mole, which is known. So for the standard enthalpy of phase fusion enthalpy of water at 273 Kelvin temperature is 6 kilojoule per mole. The delta fusion H minus is the enthalpy of fusion in a standard state. So this is the enthalpy of fusion. At standard state. The enthalpy change that accompanies melting of 1 mole of a solid substance at a standard state is called the standard enthalpy of fusion or molar enthalpy of fusion. That is called the delta fusion H minus. Now, melting of a solid is endothermic. So, all enthalpies or fusion are positive. So, delta fusion H minus is positive. So, heat is required. Water requires heat for evaporation. At constant temperature at its boiling point TB and at a constant pressure, if we go from H2O liquid to H2O gas, we will be having delta vaporization of H minus is equal to 40.79 kilojoule per mole. So we have H2O in liquid form. We'll go to H2O in gaseous form. That's why that means it will vaporize it. Now for vaporizing it at its constant temperature, at its boiling point, TB. TB is the boiling point of water, that is 100 degrees Celsius. So at TB, that is 373 Kelvin temperature, and at a constant 1 bar of atmospheric pressure, we have the delta vaporization of H. Is 40.8 kilojoule per mole. So delta vaporization of H is the standard enthalpy of vaporization. The amount of heat that is required to vaporize 1 mole of a liquid at a constant temperature and under standard pressure, that is 1 bar, is called is standard enthalpy of vaporization or the molar enthalpy of vaporization. Now there is also another question, that is sublimation. Sublimation is the direct conversion of a solid into its vapor. So from solid to gas, we will not go via the liquid phase. Directly from solid, we'll go to the gaseous phase. Solid CO2 or dry ice, it is sublimes at a 195 Kelvin temperature. The delta H sublimation value is 25.2 kilojoule per mole. Also, naphthalene sublimes slowly, and for this, the sublimation value is 73 kilojoule per mole. So here we will define another delta vaporization for sublimation, enthalpy change. It is termed as delta sublimation H minus. So for sublimation, we have the solid CO2 data. Solid CO2 or dry ice. Its sublimation value is 25.2 kilojoule per mole. At 195 Kelvin temperature. We have also naphthalene, that is C10H8, which is an aromatic hydrocarbon. The structure of naphthalene is this one. 2 benzene rings fused to one another, which is naphthalene. So we have naphthalene whose standard enthalpy of sublimation is quite slow, and the value is 73 kilojoule per mole. And also, so we have also defined another term, that is delta sublimation H minus, the standard enthalpy of sublimation. It is the change in enthalpy when 1 mole of a solid substance sublimes to its gaseous phase at a constant temperature and standard of 1 bar of atmospheric pressure. The magnitude of the enthalpy change is depending upon the strength of the intermolecular interaction that I have mentioned earlier, undergoing the phase transformation. So in case of water, there are very strong hydrogen molecular bonds present between these water molecules that hold them tightly in a liquid phase. For an organic liquid, that is acetone, which does not have a polar hydrogen, the intermolecular dipole-dipole interactions are significantly weaker. So it requires very much less heat to vaporize. 1 mole of acetone then does it to vaporize 1 mole of water. That's why I have taken up the table. It will be easier for you to understand why in case of acetone or benzene or CCl4, the value of vaporization is lower, but in case of water, the value is quite fire. Now we will try to solve a numerical problem based on our understanding till now on delta H vaporization, delta H sublimation, and all the standard enthalpy change procedures. So we have a person who is coming out of a pond which has a film of water weighing about 18 grams. So 18 gram of water of film is actually on the boy who is coming out from the pond. How much heat must be supplied to evaporate this water at 298 Kelvin? So he is coming out of a pond after having a good swim, and 18-gram film of water is around weighing around his body. So we have to must supply heat to the boy to evaporate this water. The internal energy of vaporization at 100 degrees Celsius should also be calculated for here. So the delta vaporization of H is given for water at standard state is given for the numeric, that is 40.66 kilojoule per mole. And it is given at a temperature of 100 degrees Celsius. So at 100 degrees Celsius, the delta vaporization of H minus is 40.66 kilojoule per mole. Now we have to represent the entire process of evaporation as 18 gram of water liquid will be transformed to 18 gram of water gas. So 18 gram of water's molecular weight is 18 gram per mole. So 18 gram of water means 1 mole. Now we have water in liquid phase. The transformation is from H2O liquid to H2O gas. So from H2O liquid, we have gone via phase transformation to H2O gas. So we are having H2O as 1 mole because it is said in the numerics that we have 18 gram of water, that is 1 mole of water. So delta vaporization of H is delta vaporization of U plus P into delta V. So firstly, we will write the equation, that is delta H is delta U plus delta NGRT. Now, since we have to calculate the delta U vaporization, because the question demands the change of the internal energy of vaporization at 100 degrees Celsius. So we have to calculate delta vaporization of U. In standard state, that is minus. So it is delta vaporization of H minus of delta Ng into RT. So we have this equation now. The delta vaporization of H minus is given as 40.66 kilojoule per mole. Now we have to calculate the second term, that is the delta NGRT. What is delta NGRT? So we have to calculate over here first delta Ng. Delta Ng is 1 because on the right hand side we have a gaseous molecule H2O. On the left hand side we have a liquid molecule of water. So on the left hand side we do not have any gas left. So delta Ng will be 1 minus 0. That's why we have delta Ng as 1. The capital R value is 8.314 joule per mole per Kelvin. and T value is given at as 100 degrees Celsius. It is 100 degrees Celsius, so it will be 373 Kelvin. But remember here that I have also made you cautious on the last day's discussion that this delta vaporization of H value is given at kilojoule. And now you are calculating this delta NGRT in joules. So either you have to make this kilojoule to joule first, or you have to make this joule to kilojoule first. So either one of which you have to change to a common unit. So here, instead of doing this, we will transform this delta NGRT value into kilojoule. So here, to make it kilojoule, we will multiply this delta NGRT by 10 to the power minus 3. Then this kilojoule will be cancelled by kilojoule. So we have delta vaporization of H value as 40.66. Delta Ng value is 1. R value is 8.314. Temperature is 373 Kelvin. And we will multiply this entire thing by 10 to the power minus 3 to make it kilojoule. So if we calculate this by a calculator, you will see this term is actually 3.10. So we have 40.66 minus 3.10. So which is around 37.56 kilojoule per mole. So this is the amount of internal energy for the transformation of 18 gram of water in liquid phase to the 18 gram of water in gaseous phase. That is the internal energy of vaporization at 100 degree Celsius. So what we learned in this class? In this class, we have learned about different kinds of delta vaporization of H. We have also learned about delta sublimation of H. And also in the first example, I have shown you there are different enthalpy of combustion. Delta H combustion, delta H fusion, delta H vaporization, and delta H solution. Also, we have learned about delta H sublimation, where from solid state, we have gone to directly to the gaseous phase. And in the last problem, I have tried to solve a typical problem where from 18 gram of water liquid has gone to 18 gram of water in gaseous phase. We had an equation that we learned from the first law of thermodynamics, that is delta H is equal to delta U plus delta NGRT. So from this, we have to calculate the delta U, that is delta vaporization of U minus, that will be delta H minus delta NGRT. Delta H is given from the equation, which is given, but we have to now see the R value is known to us, that is 8.314 joule per mole per Kelvin. The T value is known to us, that is 100 degrees Celsius. In Kelvin, we will express it 373 Kelvin. But here, we have to calculate the delta Ng first. And that's why I repeatedly tell you to firstly balance the chemical equation. Then only you will be able to calculate the delta Ng. The equation is this one, H2O liquid to H2O gas. The delta Ng value is 1 minus 0 because liquid components will not be considered here. So it will be 1. And now if we have got all the data of the components, delta vaporization of H, delta Ng of RT, now we can easily calculate the delta vaporization of U in the standard state. So in the next class, we'll talk about the standard enthalpy of formation of different molecules, be it solid, be it liquid, or be it gas. And then we'll also be trying to solve some chemical problems on this, numerical problems. And then we will move forward to our discussion on the Hess's law of constant heat summation. So if you have any query or question regarding any of the slides, you can go ahead and ask.